So, we had finished up last time talking about power issues, right? Again, thinking about power as the long-term probability of rejecting a null given a particular effect size, alpha level, and sample size. Tamara, can you kind of tell me, sort of explain to me sort of what this means in terms of power, how we're thinking about power, or why power is important?
Because it helps us, or it gives us more information about the analysis that we've done and maybe how reliable our predictions can be.
Okay. You're on the right track. What I would say, and we'll talk about this in a moment, we would hopefully not be using power to talk about the analyses that we run, right? I would say that we're hopefully using power to talk about the analyses that we plan to run, think that we will be running down the road, right? So let's say, CJ, I've powered my study, I have an adequately powered study, power of 0.8, and I've got a good read on the population effect, and I've got sort of a well-powered study. Am I guaranteed to find the effect that I'm looking for?
No.
No, why not?
There's still a 0.2 in there. I mean, this is helping control for type 2 error, right?
What's that now?
It's helping control for type 2 error.
It's helping
right?
control for type 2 error, right? But the thing is, if this is the distribution of all possible test statistics that I can get, right? I'm still going to have things that come on down here, and I'm still going to have things that come up here, right? So just because I've had something that's appropriately powered doesn't mean that I'm guaranteed to find an effect, right? I'm just, based on the data available to me, my best available information, I've generated a large enough sample that says most of the time, assuming this, all my parameters are correct in terms of my inputs, that I should probably find the thing that I'm looking for, right? So, if we're thinking about what does power look like in terms of sort of actual, sort of real life example. So let's say stereotype threat stuff, right? This is interesting. As we talked with Sean and Ben, which I think stereotype threat is sort of kind of questionable on whether or not this really happens. But let's pretend that it does, right? And so what we see is we're running a study is poor performance on a math test among white males informed that Asian students generally perform better. So we've got two groups. We've got a control group and we've got a threat group. The control group, we don't tell them anything. The threat group, we say, hey, Asian men tend to do better on this than you, white dudes, and then let them go through and take the test, right? And what we find in a sample of 20, we see that, in fact, consistent with our hypothesized stereotype threat, that our control group is performing, on average, better on this exam than the threat group with relative standard deviations. Okay? So what we would do to determine, sort of demonstrate power, okay? We could randomly select, and let's say that these are the real population parameters. If we were to do this sort of a billion times, sort of actually in the universe of people who are in the control, under the control condition or the threat condition, let's say the average performance in the population for the control is 9.64 and the threat is 6.58 with relevant standard deviations here, okay? If we were to go through and select 20 observations from a population of scores having a mean of 9.64 and a standard deviation of 3.17, okay? So I've got a random selection of scores from a distribution having a normal distribution having a mean here, standard deviation here. And then I randomly select 20 observations from a population of scores with a mean of 6.58 and a standard deviation of 3.03. So I randomly selected 20 observations from a population with this mean standard deviation. Okay? And then what I'm going to do is I'm going to go through, calculate, and record my t-statistic for the difference in means. And I'm going to do this over and over and over and over and over and over and over again. Okay? And what I would do is if I then plotted the frequency of the distribution of t-statistics, right? So essentially what I've done is I've run 1,000 replication samples of samples of size 20, pulling from a distribution with a mean of 9.64, standard deviation 3.7, and my second sample pulling random selection, random 20 scores from a distribution of 6.58, and a standard deviation of 303. Run the test statistic. So I actually run my t-stat, and then I just do that 100 or 10,000 times, and then I go through and plot this out. What I would do to look at power, right? If I go through and I look at the critical t-value of 2.042 for 38 degrees of freedom. Again, independent sample t-test. I've got 20 in my one sample, 20 in another sample. That's 40 people total. The total sample minus 2 is our degrees of freedom for our independent sample t-test, right? Gives me a critical t of 2.042. If I were to plot the distribution of test statistics that I would get over that 10,000 replications, and then I go through and say, this is a t-value of 2.024 right here. What does this area right here represent? Nick? Exactly. This is the power. Over 10,000 replications, approximately 86% of these replications that I run are doing what?
Just running the likelihood of this same sample happening.
Yeah. So these 86% of these replications. What is my decision in 86% of these replications?
Oh, to reject.
To reject a null, right? And so if I do this 10,000 times, 86% of the time, I'm saying that if we're talking about just reject, fail to reject, I'm rejecting the null hypothesis. Sometimes we're right here on the edge, right? Where my p-value is going to be close to 0.05, right? Sometimes we're going to be way here at the end of the distribution where I'm going to get a massive t distribution or a massive t statistic. But in 86% of the time, this is my power. 86% of the time, of 86% of these replications, I'm rejecting the null. Chris, what's going on down here at that bottom end?
About 24% of the time you're going to accept the null.
Yeah, well, we don't accept the null, but we fail to reject
Fail
null,
to reject
right?
null.
And so we're saying that things are inconclusive. So even though, if I look at the population, there is actually a difference consistent with the stereotype threat. People in the control group are scoring higher than those in the threat group about 24% of the time, or 14% of the time. I'm not finding this effect, right? And sometimes it's really marginal. It's right there, like 0.054. Sometimes down here it's like very clearly sort of not, so they're exactly sort of equal, right? But again, hopefully this starts to help sort of generate this, develop this idea of power that even if we have an adequately powered test, even if all of our estimations are sort of our estimates at the point of the effect size of the population is correct, sometimes we're just going to fail to reject just because we're kind of down here in this tail. Okay. People kind of see sort of the demonstration just from an applied setting, sort of how this idea of power is working. Yeah.
So you're doing the power before you're doing the data
Yeah.
collection. What happens if you're in a larger percentage? Would you just nix the experiment or go back to the
Okay. Hold on to that because we're gonna talk about sort of what happens when our best laid plans fall apart. Okay. So hold on to that for right now. So if we're looking at how many t-values or t-tests here in this distribution over 10,000 replications fall beyond our critical value, about 86%, and this is going to be our power, right? And so again, thinking about power being the long-term probability of rejecting the null when the null is false, that's sort of what we've got going on here. We can also think about power, and this is a little bit harder to think about, or it gets a little bit more tricky until you kind of got it set in. You think about power in terms of overlapping distributions, okay? We can think about this as the percent to which your null and your alternate distributions are overlapping with one another, okay? So if we look at this figure, and we think about this distribution, okay? This is your sampling distribution under the null here. This is your sampling distribution under the null hypothesis, right? This is the sampling distribution of your t-statistics when group 1 and group 2 are sort of actually identical, right? And so even if, tomorrow if I'm looking at this, this is the null distribution, and the mean of population A and the mean of population B is in fact identical, right? There is no difference. With the distribution, my sampling distribution, my t-statistic, will I always be able to reject that null hypothesis? No. Sometimes I can get weird stuff, right? Sometimes I'm going to reject the null hypothesis, right? And so even if, sort of under this distribution, we're saying, in this scenario, the null is true, right? But there are, again, sort of a small proportion of tests that are going to fall at the extreme end of that tail, even when the null is true. And this is what we said in our hypotheses test as our critical region, right? Assuming the null hypothesis is true, it would be very unlikely that we would get these data. It's not impossible. It happens sometimes, but that's going on down here in our alpha region here, okay? So this is our null distribution. We also have a sampling distribution of the mean when the null is false. This is my H1 distribution here, okay? And in this situation, Chris, if, let's say that I actually do have, say, a 6-point difference, the mean of my group 1 and the mean of my experimental group are actually 6 units apart, so that the null hypothesis is false, right? Am I always going to get a t-distribution, a test statistic that tells me that the null hypothesis is false? No. No, sometimes I'm not. Sometimes I'm going to get things that could tell me things in the opposite direction, that sort of my first population is sort of different than the other one in the opposite direction, right? But if we go through and we take our null distribution and we overlay our alternate distribution, we can use this to think about, sort of as a different way to think about power, okay? So if we're looking at our sampling distributions here, the area in my null distribution, in my alternate distribution to the left of alpha, this is beta. Someone help me out, what's beta here? What's happening? So if this is sort of my t-scores, right? And this is my null distribution, this is my alternate distribution. What's happening in this gray area right here?
We're failing to reject the null.
Yeah. I'm failing to reject the null, right? So so this is true, right? My alternate is true, right? The null is false, right? But as I'm looking at the distribution of t-statistics, possible t-statistics, for even given that these two things are different, there's a good chunk of the t-statistics that I'm going to get that are still going to fall below the threshold of my null distribution. And what I'm going to do is I'm going to be able to reject the null, even though the null is true. These are my type 2 errors. Beta is my type 2 error, right? This is all the stuff right here where I've made a type 2 error, right? These t-statistics are still coming from my alternate distribution, but the t-statistics on this alternate distribution are still falling below, on the null distribution, my threshold for, or my benchmark for claiming statistical significance. And so what I'm going to do is I'm going to make a type 2 error. I'm going to say that there's, I'm going to fail to find evidence against the null when sort of the null is actually false, okay? And if I'm looking at the area of my alternate distribution that's to the right of alpha, right? So what is this telling me right here? What's happening in this section of my alternate distribution?
One of the distributions it's not happened, and there's nothing to talk, or like it's.
So if I get a t statistic in my alternate distribution here that's in this region, what's the decision I make?
Would the alternate hypothesis be true? Or?
Yeah, I would reject the null hypothesis. We don't, again, sort of accept the null or sort of accept the alternate hypothesis, right? But what we would do if we have a t statistic in this area is we would just fail, or we would reject the null hypothesis. And so this right here, this is our power, all right? And so if we think about, CJ, if you're looking at this overlapping distribution, is our experiment, what do I conclude about the power of my experiment based on these overlapping distributions here?
Got quite a lot of errors in there.
Yeah, right, so what would I say, what does that tell me about my power?
It's pretty low.
Yeah, exactly. This is what happens when I have low power. I have an effect, there's an effect there, there's an effect in the universe. But what ends up happening is my alternate distribution that I'm actually gonna get in terms of my t-scores is hugely overlapping with the null distribution. And so as a consequence, even everything in this distribution here is stuff that I'm getting, right? It's just that a lot of the test statistics that I get within that distribution are still sort of gonna fall below the critical value set in the null distribution, and so I'm gonna fail to reject, okay? But if I go through and I up the difference, let's say that my effect size here is much larger, okay? Alicia, what's going on here with this in this distribution? So if we're saying that this is my critical value under the null hypothesis, right? Here is the distribution of my test statistics from what's actually going on in the universe, right? What is this gray area right here? What's going on if I get a test statistic sort of in this area in terms of my decision? Rejecting the null or failing to reject the null, right? So once again, this dark region here, this is where I've made a type 2 error, right? Even though sort of this is sort of the data that I'm pulling from are actually, the means and the populations aren't the same. They're different, and they're quite a bit different, right? But still, some of the times, I'm going to fail to reject the null because they're just at the bottom end of the distribution, right? Chris, what's going on in this area up here?
You're rejecting the null.
I'm rejecting the null. I'm making the correct decisions, and this is my power, right? And so what's the difference between sort of, relative to this scenario, what's the power of my test in this scenario?
As observed, is substantially more.
It's substantially better, right? On average, if this is the average test statistic that I'm going to get out of this distribution with sample size 20 and alpha 0.05, the modal test score, or the modal test statistic that I'm getting out for this is going to reject the null, right? Sort of on average. Now, I still wouldn't say that this is probably isn't equal to an adequately powered test if we're saying power is, defining adequately powered test as power equals 0.80. This looks like more than 20% of the distribution, but it's still a lot more, I have a more powerful test than what I've got right here, right? So again, when we're thinking about power, there's two different things that could be going on here. Now in this situation, what we've done, and we'll talk about this in terms of confidence intervals around our effect sizes, we've increased the effect size. Here the effect size is functionally equivalent to a difference of 6 points, here it's a difference of 10 points. So I'm looking to find an effect that's larger in this scenario than the other scenario, okay? What's the other thing that I can do to get more separation between these two distributions? Increase my sample size. Because what happens when I increase my sample size? So what increasing my sample size does what to my standard error? What's that? It decreases it, right? And what is my standard error? What is standard error?
The variability from
Of my population sampling distribution, right? So I could have a scenario where I've got a scenario where the difference, this is my null, delta eventually, right? But what ends up happening if I have a low number of people in my sample, right? The distribution, my test statistic, is really wide, right? My standard error is big. The standard deviation of my sampling distribution is pretty wide, right? But if I bump up, my sample size, I go from a sample of 20 to a sample of 200. What does this do to the variability of my sampling distribution? It makes it smaller, right? So now all of a sudden, I've got a distribution that looks something like this, and a distribution that looks something like this, right? So the difference didn't change. The effect size is still the same across these two scenarios. But in this one, I have a sample size of 20, so my standard error is big. So the variability of my sampling distribution is quite large, which ends up being a considerable amount of overlap, right? If I go through and I increase my sample size, the standard deviation of the sampling distribution decreases, or my standard error, and now all of a sudden in this scenario, we see that these two distributions are actually minimally overlapping, right? Again, the effect size stays the same. What's happened is I've just changed my standard error and increased my power. So we can think about, in this example, what I've demonstrated that we've done is we've changed the effect size. But we could also see this same kind of thing if I increase, say this is a sample size of 20 and this is a sample size of, say, 50. It's going to shrink that down and cause less overlap between those two. Questions about this? Yeah.
So beta, is it functionally just your probability of type 2 error? That's it? All right, cool.
Alpha is your type 1 error, beta is your type 2 error, right? And so this is why we say you'll see power indicated as 1 minus beta. So 1 minus your potential for type 2 error is going to be your power. Other questions? All right, cool. So influences on power, effect size, right? The magnitude of the difference between my null and so what's actually going on in the population, greater effect sizes, greater power. Alpha level, if I can increase my alpha level, increases my power. So if I go from 0.05 as my alpha, and if I wanted to say I want my alpha to be 0.10, that would increase the power of my test. That probably wouldn't fly with the journal publication. But there are situations where you could make that argument. And in medical science, there's more of this type of thing, right? If I've got an intervention that is potentially important, and the side effects are sort of pretty minimal, I could make an argument that, hey, I wanted this initial pilot, I wanted to set my alpha level to 0.10 because of pros and cons, right? Now, if I have something that's, like say, a cancer treatment that's potentially could be effective for intractable disease, but it also has incredibly severe side effects that could include death or something like that, then I might want to crank the alpha level way down because I don't want to say that this is an effective thing if it's actually not, right? The types of things we do, we generally can't play around with alpha levels, but there are situations where you could make strong arguments for that. Population variance, right, is a variability of our sample distribution of sample means increases the variance of, is the variance of what I'm measuring increases. That increases my standard error just because variance goes in the numerator of the standard error. But again, we can't often impact the variance of our measures. We can with better measures, right? If I get better, more accurate measures, it's going to cut down on my error variance, which is going to sort of decrease that a little bit. There's often not a whole lot we can do here. But then we also have sample size, right? Sample size decreases variability in the distribution of sample means, which is going to be our standard error, right? Variability in the sampling distribution, this is just our standard error. If we can crank down that standard error, that's going to increase increase our power. So we don't often have an ability to impact the effect size. The effect size is what it is. Now we can do different types of things. We can do like extreme group designs, right? Where I'm taking a hypernormal group and comparing it with a very severe group. That's going to increase your effect size, right? If I have a question on whether or not people with PTSD are different than people without PTSD, there's some variability there, right? If I wanted to increase my effect size, I might say, oh, I want people with severe PTSD against people who have never meet no criteria for any diagnoses and are 0 on all things. That's going to make that effect size a lot bigger. The concern with extreme group designs is that we might get things that aren't actually representative of the actual phenomenon. Alpha level, can't do much about that in most cases. Population variance, better measures are going to increase the variability of our measures to some degree, but really it's going to be sample size that goes through and impacts things, right? So we need more power, increase the sample size, okay? To the extent that we can, right? Now, sometimes, particularly if we're running an intensive intervention, so Chris, like the stuff that Kyle was talking about, where you've got people longitudinally for an extended period of time, so doing some fairly intensive physiological monitoring, things like that, we're kind of limited to what so we can. Not every study is amenable to having sort of 1 million people in the sample, but to the extent that we can think about and plan ahead to know kind of what the size of the sample is that we would need to adequately power things, this can go through and be helpful. Okay, so again, this is the theme here, is we're talking about doing things on the front end before we collect our data, before we get sort of committed and then realize that our study is doomed to failure because it has impossible power. All right. So what we want to do, if we're going to go through and we're going to run power calculations, we need an estimate of our effect size. Okay. Number one thing we need to have. If we're going through and we're going to do this, our number one source and sort of the best case scenario is we go through, look through existing research to see if we can start to pull for the effect that I'm looking for. What's the general magnitude of this effect that people have found in the past? This is important. Why it's so crucial to report mean, standard deviations, relevant statistics in our research. Do someone a favor down the road. Report means, report standard deviations. Be a pal and just report the effect size in the document. That way it makes it easy to go through and pull things up. It's frustrating. You guys will want to smack your head against a wall. Eventually, you're going to have to put together a power analysis for a thesis or dissertation, and you're going to be combing through the existing literature and find out that dum-dums haven't reported means, standard deviations, test statistics, so that you actually can't estimate the effect size that they've got. You'll be incredibly frustrated, and it will sort of motivate you to pay it forward and sort of do this in your own research. So we can, in the best case scenario, go through, take a look at what effect size we're looking for, and then use that for our power analyses. Okay? But sometimes we're going to go through and we're not going to be able to find existing research that does this. Either people haven't reported appropriate statistics for us to derive effect sizes for that, or maybe no one's done it. Right? There's just no one has actually sort of looked at this or at this specific thing or the specific question that I'm looking at, which is possible, right? What we could do then is we could ask ourselves, how much of an effect size is needed, okay? How much of an effect would I need to see in order for this to be meaningful, okay? And so this starts to get into that idea of practical differences or practical effects that we've been talking about. So let's say that I'm interested in some skills training sort of intervention for GRE, right? And I'm saying, I need this intervention, given the time and effort and sort of what I'm going to charge people to go through and do this, I need to see an increase in 40 points on the GRE, okay? So with a standard deviation of 100 for the GRE, we'll say I would need to find an effect of 0.4. If this is going to be useful, right? Anything less than effect size, anything less than a 40-point increase is not going to be meaningful. So what I'm going to do is I'm going to power my test to detect an effect size of 0.4. Because you know what? If the effect size is not at least at this level, if it's 0.2, then it doesn't matter anyway whether it increases it by 20 points or not, because who cares, right? And so what I can do there, and so if I think about this in terms of treatment types of stuff, right? We could do this, if we say best practice intervention, existing intervention, treatment as usual, results in, on average, based on our meta-analyses, an effect size of, say, 0.8. So it's a large effect. So that's on average, right? And so if I'm going to put together a new treatment and introduce it into the world and sort of stand behind it, it's got to be at least getting the same level of effect with what we're seeing with the stuff that's already out there, right? And so what I might do, perhaps this is my unique treatment. There's no one else who's ever actually looked at this before. What I might say is, well, I'm going to power my test to an effect size of 0.8, because if it's below that, it doesn't matter if I detect it anyway, because this is what it needs to be in order to be important. Okay? We'll see what how we're changing this about here. Other thing we can do is we can use conventional cut points. This is what we do when we don't have anything else available to us, right? So let's say I'm running, which is what a lot of our research is, a lot of what my research is psychopathology research, right? We're testing mechanisms and theory and things along those lines, right? So it's kind of hard for me to say, like, tell me what a practical effect size is. Well, I don't know. It's sort of testing theory and this idea that this is kind of how these mechanisms work, right? I'm looking to the extent to which something moderates the relation between X and Y. I don't have a basis for saying sort of in random sort of measure points how much of an effect is. I just sort of want to see if the theory is correct, consistent with the data that I've collected, right? What I might do then is just say, well, what I'm going to do, if I'm going to be conservative, I'm going to power my test to detect a small effect, right? Because if it's less than that, then I don't know. So, but what I know is a small, medium, and large cut points. What I'm going to go through, and I'm going to power my test to say, so well, this is where we're at. So this is what we did with Ryan's dissertation, right? He's testing whether or not data are consistent with a newish theory of suicide ideation and activation and things along those lines. No one's ever actually looked at this stuff before. So how do we power the test? Well, he's looking for an interaction effect, which we'll talk about. Those tend to be pretty small. We're just going to go ahead and assume that what we're looking for is a small effect size, power the test to that, and then say this is the sample size that we would need to detect a small effect in this study, at least 80% of the time. Okay. Now, where things get into difficulty is when you say, CJ, I'm sitting on CJ's committee, and CJ says, well, random power analyses, but there's no one else has ever done this before, and it's a tested theory, so I don't know, but I'm expecting a large effect size, so I need 40 people in my sample. Like, So based on nothing, you're assuming that you're going to get a large effect size out of this, right? This is where, if this is where you're at, probably you need to be the types of effects that we find in social psychology or in social sciences. What are the effects that we're generally working with? Large, small, medium-ish? Small to medium, right? Because the stuff that we're looking at is small. We've got a ton of error in our measures. We've got a ton of individual differences in terms of where people are at or all over the place. Free will gets in the way all the goddamn time, right? And so generally the types of things that we're looking at are small-ish effects, right? So what you want to do is not, the concern is to start basing your estimate of what you're expecting in terms of effect based on how many people you want to collect. And if that's what you're going to do, just collect the minimum amount of people that you want to collect and don't even pretend that you're doing a power analysis, right? So just be careful when you're doing this, right? Hal, in a text, when he's talking about effect size, says, I don't know, often translates into I hadn't thought that far ahead in terms of sort of what the effect I'm looking at. I would say I can't, means I didn't try very hard, right? So going down through, and you can go through and pull based on stuff, right? So it might not be the exact effect that you're looking for, but in general, this is what we had to do with Layla's thesis. Well, these are kind of, her question is different than what people have done, but in general, this is kind of what people have gone through and looked at. And so they're using some of the things we've talked about here, be able to take test statistics and reverse engineer that into a rough estimate of effect, using mean standard deviations to calculate stuff. Someone's given an R, and you need that to be a D. going through and using some conversion stuff to sort of get that back. So at least you got sort of that horseshoes assessment of where things are at, right? Because remember, when we're talking about power analysis, it's much more kind of this general area as opposed to kind of this general area over here. Questions on this? All right, cool. So when we're thinking about calculating power, right, we know that our test statistic, and we're going to take a simple case here, we're talking about a single sample test. Single sample test, single sample t test, or single sample t distributed around 0 as long as the null hypothesis is true, okay? So as long as the null is true, our test statistic is centered on 0, right? If my novel population that I'm interested in looking at, the mean of that novel population really is no different than the reference population, then on average, my test statistic is going to be 0. Sometimes it's going to be above, sometimes it's going to be below, but on average, it's going to be sort of about 0. Okay? But if the null hypothesis is false, what ends up happening is my test statistic, my t statistic is no longer centered around 0 because I'm subtracting the wrong population, right? I'm taking my sample mean that I've expected, subtracting the mean expected under the null, but my population mean is bigger or smaller than the null, and so what ends up happening is my t distribution isn't centered on 0 anymore, because it's going to be different, right? It's shifting around. And the point at which that t distribution is centered, we're going to call that delta. Okay? This is lowercase delta here. That's this point right here, right? And if we're going through this shift from 0 under the null to delta, wherever the alternate hypothesis is, we're going to refer to this as the degree of non-centrality, okay? And delta is going to be your non-centrality parameter. This starts to become important when we're talking about power, when we're talking about calculation of confidence intervals around effect sizes. What we want to do is we need to figure out what that non-centrality parameter is, and we need to determine whether or not, so what the sort of confidence intervals are around that, okay? And so if we're thinking about it this way, we think about power as how likely we are to find value of the non-central distribution that's greater than the critical value of t under the null, right? So we had talked about this H1 distribution as our alternate distribution. We can also talk about this as a non-central t distribution. And the non-central t distribution has some different properties that we'll get into when we're talking about confidence intervals around effect size. But the idea, and again, this is why thinking about power in terms of overlapping distributions is helpful, because what we're actually asking here is how likely are we to find a value of this non-central t that's centered around delta that actually goes through that's greater than the critical value here. So in this case, this part here, where my power is, this is the part of my non-central distribution. These are values within my non-central distribution that exceed the critical value under the null distribution, and this is my power. Okay. So this is kind of heady in terms of overlapping distributions and things along these lines. People kind of getting a sense for what's happening with some of this. Okay. All right. Where are we at in terms of? Okay, cool. We're trucking along. All right. So if we're going to go through and calculate power, sort of old school by hand types of stuff, what we would be doing is looking at calculating power based on tables that I gave to you previously, looking at specific values for my non-centrality parameter and alpha, okay? So this power table that you've got right here, take a look at this, and what we've got is, you can see, so this is alpha for my two-tailed test, so I've got 0.1, 0.05, 0.02, and 0.1. So we're going to be working with 0.05, that's just our standard alpha level for our two-tailed test, right? And then in our left-hand column, you'll see that we have delta here, okay? This is our non-centrality parameter. And so what we're going to do here is we're going to calculate our effect size again, for our single sample, our reference mean, or the mean under the null, divided by our standard deviation. We just got one standard deviation, so effect size for single samples is easy. And then we're going to calculate our non-centrality parameter as our test, or our effect size times the square root of our sample size. Okay. So let's say we want to know whether people seeking treatment for psychological problems have higher IQs, right? We've got crazy geniuses running around, right? Like, oh, everybody who struggles with stuff, they're actually higher IQs, right? They're overthinking things. In fact, you've overthought things too much. If you just dumb it down, like, you'd be fine, right? So let's say that we go through a sample of 25 individuals, and we find that their IQ is 105, okay? Our reference value for IQ is 100, standard deviation of 15. So what we go through and take a look at 105 minus 100 divided by 15. So our effect size, we get an effect size of 0.33. Okay. Chris, give me an interpretation of this effect size.
Effect size. So people seeking treatment for psychological problems have a third standard deviation higher on average than people not seeking treatment for psychological problems.
Okay.
So I guess 5.
Who's our reference group here?
I guess people not seeking treatment for psychological problems. I guess just that it's average IQ scores.
Yeah, there you go.
Okay.
Perfect, got it. Right. So our normative, like, we don't
Yeah.
know whether or not people are seeking treatment or not. They're just sort of the norm of the general population, right? And so that was beautiful, right? We're in general sort of our effect size is saying that based on the data that we've collected, we're saying that people seeking treatment for psychological problems are scoring on average about a third of a standard deviation higher than the normal population.
Is it okay in this situation to just be like, I scored 5 higher
What's
on
that?
average? Just because a third of the standard deviation is 5?
Yeah, yeah. And for that, if you're working with someone who is familiar with IQ scores and things like that, 5 points higher might make some sense to that person, just in terms of the raw metric.
Oh, okay.
Right? But maybe not, right? And just in terms of reporting things in terms of standard deviation units, because I know what a standard deviation from the mean means, and I know what 2 standard deviations and 3 standard deviations. It just sort of converts things into a metric that just communicates more information in general, right? But you could, if you're sort of talking to, say, Tara, and you say, oh, this group is scoring about 5 points above the population mean on stuff, that would probably mean something to her, less to me. So that's sort of why we're thinking about doing some of this stuff. Okay. But what we would do then to get our delta is we would go through and take our effect size, multiply the square root of our standard deviation. And what we would do then, if we go through and take a look at our power table here, is I would go through and I would say, for this example, delta is going to equal 1.65. Okay, so I take 0.33, multiply it by 5, right? I get 1.65. If I go down through and I take a look at delta of 1.65 on my table here, and so it goes 1.6, 1.7. I go over to my two-tailed, or my alpha level 0.05. It looks like my power is going to fall somewhere between 0.36 and 0.4 on that table. People see where I'm getting those numbers from. Okay. So here, because 1.65 is sort of equidistant between the two, I would then say that, assuming that the null hypothesis is false, I would say that my effect is expected to reach statistical significance about 38% of the time, given a sample of 25 and a population effect of 0.33. So my power here is about 0.38. Okay. So am I making my pumped about my power in this test? No, I'm not, right? Pretty bummed out about that. So what I might say is, well, how many people do I need then to adequately power this effect? So I've got a 5-point difference, right? 25 gives me power of 0.38. Assuming that this effect size is accurate, how many people would I need to actually adequately power this, right? This is nice. It ends up just being sort of a small reorganization of your, there's a little bit of algebra will get you that. So if I want to look at to say what's the sample size, what's the sample needed to achieve a power 0.80, my sample size is going to be equal to my delta over my effect size squared, right? I'm just rearranging this formula right here, okay? And so it's going to be n equals 2.80 over 0.33, and I'm going to square that, okay? Where did I get 2.80 here? Yeah.
0.8 divided by 0.33.
What's that now?
So your ideal power value, which is 0.8,
Mm-hmm.
and divide by 0.33.
Okay, so where did I get this? Yep, we're gonna get that. Where did I get this delta value? Where did I decide on 2.80? You see that? What's that? The table. Yeah. And so where you, Nick, what are you seeing on that table? Where's that 2.8 coming up with?
0.80 was corresponding to alpha 0.5.
Did I misunderstand you?
Yeah, just do it like numerically. It's supposed to like look at the table.
Okay, yeah. So if we go down through and take a look, so we actually don't have to, oh, I see what you're, okay, I see what you're saying. Yeah, sorry. Yeah, okay, you did it, yes, you can do it that way. No,
I
sorry.
should be more clear about it.
No. I, to be more insightful on things. But yeah, so going down through and taking a look at the table, right? So if we take a look at our power table for alpha 0.05, we drop down and we look at 0.80, because that's adequate power. And if we go down and look across, looking at adequate power is associated with a delta of 2.80. So anytime we're calculating sort of what's the sample we need to get a certain adequately power something, tomorrow what's delta going to be equal to? 2.80. Okay. So if we do this, if we go and take our sample size 2.80 divided by 0.33, and then we square that, we end up with a power and about 72 for adequate power there, right? With our power calculations, if it says 71.34, we can't have 3.3 of a person, so we just kind of round up to say about 72 people. Questions on how we kind of did how we worked this backwards by hand? All right. So same type of situation for our independent sample t-test. Assuming that we have a balanced design, we've got equal sample sizes here. So group 1 and group 2, equal sizes. And we're looking for the power to detect difference in sample means. So our sample, or our effect size, is going to be, again, mean 1 minus mean 2 over some sample variance, or sample standard deviation. Okay. Tomorrow, what are my options for my standardizer here for an independent sample test? Do you remember off the top of your head?
What do you mean?
Okay. So for our single sample test, we only have one standard deviation in the whole thing that we can play around with, right? But with our independent sample test, we got the variability of the standard deviation in sample 1, variability of standard deviation in sample 2. What options do we have in terms of creating an effect size?
If you have equal sample sizes, we can just average.
Yeah, we could average. In general, what would we typically think about that is? The pool, right? And probably for this is what I'm probably going to want to use the pool standard deviation for this in terms of calculation of power, right? So if I go through and I take mean 1 minus mean 2 over my pooled standard deviation, we get my effect size, and then delta is going to be equal to my effect size multiplied by n over 2, where n is the number of cases in either sample. Again, we're working with equal n's, so it really doesn't matter. The thing you want to make sure that you're taking account for here that this end is not sort of the total end. So if I've got 20 people in sample 1, 20 people in sample 2, this isn't 40 over 2, it's 20 over 2 when you go through and calculate this. Yeah.
What happens when they're not?
Okay, we'll get to that.
Okay.
Yep. Okay. So in this equal samples here, what's the difference in the means, symptom means for treatment 1 and treatment 2? We see the average difference across treatment 1 and treatment 2 is 5, and we've got a pooled standard deviation estimate of 10. Okay, and we've got 25 individuals in each sample. My D is going to be 5 over my pooled standard deviation, giving me an effect size of 0.5. Multiply that by the square root of 25 over 2, which is going to give me power of about 0.43. So if I go through, actually calculate that delta, I'm going to get delta of about 1.77. Okay, and if I go down through and identify delta about 1.77, it's between 1.7 and 1.8. I've got somewhere between, power is falling somewhere between 0.40 and 0.44, so I'm going to say it's closer to 1 instead of about 0.3. So assuming the null hypothesis is false, my effect is expected to reach statistical significance about 43% of the time, given 25 people per group and population effect of 0.5. Same thing, we can go through, back translate, sort of rearrange this algebraically to get the number of people that we want to achieve adequate power. Again, our 0.43 is better than what we had before, but it's less than a coin flip, right? And that's kind of a bummer. So we go through and we take 2 times 2.8, because that's our delta for adequate power, divided by our effect size, take the square of that, and we end up with a sample size of 63. It's going to be 63 per cell though, okay? Remember that what we're saying is we need to more than double the size of each one of our treatment groups in order to achieve adequate power, assuming that we're looking at effect size that's right at that median level of 0.5. So same kind of process, people kind of see, so we just played around. Where did this 2 come from? Yeah, 2 groups, right? And if we have 2 groups, what does that do to our error?
It decreases our, yeah.
So I've got error in group 1, I've got error in group 2.
Decreases the likelihood of error.
It doubles it, right? And so now do I have not sort of error in 1 measurement, I've got 2 measured levels of sources of error. And so what it functionally does are relative to our independent sample test or our paired sample test, relative to our, our single sample test or our paired sample test, relative to our independent sample tests, it doubles it, because we just have another group with a lot more errors, so we have more stuff to deal with there. Okay. So what happens if we have unequal samples, which is generally what we're working with, right? Because we don't have perfect experiments all the time. What we need to do is we need to calculate the harmonic mean of n to make an adjustment for these samples. And so what we're doing to get our harmonic mean sample size, we take 2 times sample 1 times sample 2 over 1 plus, sample 1 plus sample 2. And what this is going to do is it's going to give us our harmonic mean sample size that's going to give us an adjustment. Okay. So going back to our stereotype thread example, in this situation, we have a mean of 9.64 with 18 people in our control. Our threat condition has 12 people with a mean of 6.58. Our pooled standard deviation is going to be 3.1. Okay. So if I go through and first calculate, well, I guess we can go through and calculate my effect size. It's pretty straightforward. Control minus threat over my pooled standard deviation gives me an effect size of 0.99. Pretty excited about that. We've got a full standard deviation difference between these two. And I'm going to take this, but I've got to take my delta, I've got to take it by n over 2, or excuse me, my effect size multiplied by the square root of n over 2. But remember, because I have unequal sample size, I don't know whether 18 or 12 to plug in, and so I have to plug in my harmonic mean sample. And my harmonic mean sample size is 2 times 18 times 12, or 18 plus 12, which is going to give me harmonic mean of what is that? What is it?
14.4.
14.4. Okay, cool. So go through, plug that in, which is going to give me delta is equal to 2.67. Okay. Which is then going to say give me a power of about 0.75. Okay. So again, 2.67. Right. If I go over and look at so my power table, it's sort of in between 0.74 and 0.77. Right. And so about power 0.75. So assuming null is false, expected to reach statistical significance about 75% of the time, given samples of 18 and 12, population effect of 0.99, right? But note that my effective sample size here is less than my full sample size of 30, okay? If I go through and I take 14.4 multiplied by 2, I get 28.8. That's not the full sample that I have here, right? And what this, so what is this suggesting, Chris, about what is the impact of unbalanced designs on my power?
It looks like it reduces your power a little
It
bit.
reduces my power, it decreases it, right? And so the extent to which I have unbalanced designs increases proportionally, or reduces proportionally the power of my tests. So if I have wildly unbalanced designs, let's say I have 100 people in my total sample, right? If I have group 1 is 50 and group 2 is 50, I have much more power, assuming equal effect size, for that study than if my one sample size is 20 and the other sample size is 80. Okay. Now, sometimes what people will say is, well, should I just balance my design? Should I throw out 60 people in one group and sort of balance that out? Don't do that. That has a more serious, having a total sample of 40 is much worse for your power than having an unbalanced full sample of 100. But it still sort of comes at a cost of power when you're taking a look at some of those unbalanced designs. Okay, and then we reimburse it all to go through and determine a number of people I would need to have in my 2 samples there. Okay. Last thing we'll touch base on here is our paired sample. Okay. Paired sample is interesting because the effect size that we'll use to calculate power for our paired sample tests is not the effect size that we're going to want to use for talking about the power of our tests in terms of practical sort of interpretations and things like that. Okay. The effect size that we're going to calculate for our paired sample test is going to be mean 1 minus mean 2, or the difference of our means, right, over the standard deviation of x or sort of over the standard deviation of the difference of means, which for the purposes of power is calculated as my variance estimate multiplied by 2, multiplied by the square root of 2 times 1 minus rho, where rho is going to be the correlation of time 1 time 2. Okay? And what this is going to do, so remember this repeated measures effect that we had talked about before, the one I told you not to use because it can make things look way too big. This is basically the sort of same procedure that we're using to go through and calculate power for this test. Okay? What ends up happening is this rho ends up correcting or correlating or sort of increasing my estimate of effect, which is important because our paired sample tests are much, much more powerful than our independent sample tests. So you can think about this as being the correction for sort of recognizing that we're using a paired sample test here. So let's go back to our stereotype threat. Let's say that instead of working this in a independent sample design, right, where at least you go through and you have a group of, say, 30 students who complete a test under no threat, and then a different group of 30 people who take the test under threat, and then we compare the two. Let's say what you did is you decided to go through and a group of 30 students, have them take a test, and then you go through and then have them complete a sort of an alternate test. It's sort of equally sort of difficult, but this time under stereotype threat. Okay, and so what you've done is you've found that mean performance at time 1 is 9.64, mean at time 2 is 7.55, and you have 30 people in this in the total thing. Okay, your pooled standard deviation across time 1 and time 2 is 3.10. Right, so this is just at square root of your average variances right here. And let's say that there's a test retest across these two time points at 0.92. Okay. Here, what we would do is we would take your average variance, so the square root of your average variance, or what we call that your pooled variance. Multiply this times the square root of 2 times 1 minus your test retest here is going to give you a value of 1.24. Okay. Now, how does this estimator look relative to that estimator? Sorry. So if my pooled variance, so the average variance at time 1 and time 2 is 3.1, but I've got my different standardizer here that I calculated for my paired sample test is 1.24. What's this look like relative to this? It's smaller. What's this going to do with my effect size? It's going to jack it way up, right? It's going to make it much, much stronger, right? And so what ends up happening is the effect size that I'm plugging into my power calculations is much larger than it would have been if I would have ran this as an independent sample test, right? And so we go through, calculate delta as 1.69, which is going to be my effect size, times the square root of 30. This is just the same thing as the same procedure as our single sample test, right? This paired sample test is just a single sample test of the different scores, right? So we go through and calculate this here, and what we find in this scenario is a value for delta of 9.26, right, which gives us power about, and it's not even on the table anymore, right? It is massively powered. So basically, how often am I going to reject the null hypotheses in these data? All the time, right? And so we would say, assuming the null hypothesis is false, effect is expected to reach statistical significance over 99% of the time. Given a sample size of 30, correlation between like two measurements of 0.92 and a population effect of 1.69. Okay.
Graphically, what would the distributions look like with that? Just like so far.
Yeah. What are they going to look like?
The delta is tremendous, so it's just like so far out relative to what you're measuring.
Yeah. Or even if, and so it sort of depends on your scaling, right? But what I would get is so this and this.
Yeah.
I've basically got overlapping distributions, right? Here's my null, and here's sort of what's actually going on. This is existing in a completely different world than that, right? And so once again, this could be a function of sort of the deltas, the difference in the non-centrality parameter here, or it could be just because I've shrunk down. So even if I have like a small effect, so I'm looking at a small effect, let's say like a between groups effect of 0.3, okay? That delta isn't all that big. But if I'm working with samples of 1,000, right? So 1,000 this and 1,000 this. What's that?
It's like super peaked out, so the delta is kind of irrelevant.
Yep, so the delta is actually, my non-centrality parameter isn't sort of that wide. It's just I have no variability in that just because my stuff is so precise. So, but yeah, this is what's going on right here. We have distributions that don't even overlap based on this. And this starts to become important if, again, for clinical folks, if you're ever looking at statistically significant and reliable change, that sort of classic Jacobson and Trudeau article. looking at sort of overlapping distributions and thinking about like how far, so this is my clinical distribution of scores in people who meet criteria or sort of not good. This is my normal distribution, sort of how much overlap between these two distributions, what I need to see in order to claim a statistically significant or reliable change. Good thinking there. Okay. All right. So what's going on in the power in this sample? So I've got before, so this is not so different than the stuff that we were working with before in terms of sort of actual sort of average difference across across my two means, right? Nick, why am I getting such massive power with a sample that's only 30 people?
Partially, well, because the effect size is much higher, and that's because of the design, which reduces the error because it's paired.
Yeah.
So there's less within variable.
Right. If this was coming from an independent sample test, right? So I've got 9.64 and 7.55. If I subtract those two, I get a difference of 2.09, right? And then if I'm saying this is a regular old pooled standard deviation 3.10, and I divide that, my sample size, or my effect size, if I was calculating this as an independent sample test, or if I was calculating this effect size with how I would probably report it in a research study, I'm getting a D of about 0.67, okay? So the effect size that I should probably be reporting in my article is a decent effect size, right? So I've got 2/3 of a standard deviation difference from control to threat reduction in overall performance scores, and so this is, I'm happy with effect size if all my effect sizes were in that level, right? This is a very, very different effect size than we're plugging into our power calculation. And what's happening is we've got an incredibly strong correlation between my two time points, right? Now what happens in my effect size as my correlation starts to decrease? It goes down, right? And so this is why when we're thinking about estimating sort of things that there's some certain, so for example, some of the data that you guys are playing with, I collected for my dissertation, we're looking at pre-post and like skin conductance, right? If you look at the correlation between those measures, my skin conductance right now and my skin conductance 5 minutes from now are going to be super, super correlated. It doesn't matter sort of what I'm doing, right? Those two values are going to be collinear to the point of being like 0.9 to 0.95-ish, right? What that does is that means our paired sample test with that stuff is incredibly powerful. Like even small shifts or changes start to make for a very, very powerful design. Now, if my two measures are less correlated, right, then my stuff starts to go down. If you look at pre to post like treatment stuff, right, early treatment and sort of at the beginning of treatment, at the end of treatment, symptom measures correlated 0.6 with one another and things like that. That's still going to give me a greater power than this, but it's not going to be the same thing as something along these lines, right? So one, it's the design, and two, with how we're going through and calculating power. If I went through and calculated my power based on this, it would be far less, right? It wouldn't be an appropriate calculation of power. The formulas go through and adjust for this fact that we are running a repeated measure design, and that we're assuming that your values at time 1 are going to be correlated with your values at time 2 on average. Because if they're not, we might as just well run an independent sample t-test and just sort of call it good with that. So again, another pitch for incorporating repeated measures designs whenever possible. And this is where, again, if you're doing stuff like some of Kyle's EMA stuff, or Ben does a lot of EMA stuff. Has Sean done EMA stuff? Not yet. But this is why when you've got repeated measurements over over a time series, over a long course of time, this is why these HLMs can be sort of really, really powerful and compelling, even with relatively small samples. So in terms of our repeated measures, a lot more power relative to our between subjects designs. Remember that our repeated measures designs are sort of reducing our overall error variability. They're cutting out those individual differences. So the difference between Siley and Chris and Nick and CJ, like all the things that make you, that introduce error in terms of our experiments, we're cutting all that stuff out. Everybody's acting as their own control, and so we have much less noise in terms of that. We also see corrections as a function of our correlation between our two measurements, and as we reduce that down to zero, functionally what we're doing is we're working with an independent sample design. Okay, so again, the importance is thinking about developing studies. You've increased your opportunities to identify effects that you're hoping to find if you can go through and run this in a paired sample design as opposed to independent sample stuff. Okay. All right, cool. Let's take a break. We'll come back. We'll do some quick calculations in G-power just to show you what that looks like, and then we'll hopefully get into ANOVA stuff. We're going to go through power calculations in G-power. But then I realized that this computer will not let me download anything on it because stuff. So what I'll do is G-Power is pretty straightforward, pretty easy. I'll go through and post a quick screencast of me going through these demonstrations and just show you. Anybody used G-Power before? Okay. It's a slick tool. It's not perfect. Sean doesn't like it for understandable reasons. But in terms of just basic power calculations for pretty simple stuff, it works okay. So I'll go through, show you how to pick that, work through and pick different things, but it's all pulled down menu, pretty straightforward. So we'll walk through these examples in that screencast so you have that under control. Okay. So power write-up, okay. Effect size of D equal 0.5 expected based on existing data from Jones and colleague. Power analyses using these data indicate a sample of 32 individuals per group required to achieve adequate power, blah, blah. Okay, so, I mean, main components, you're identifying what your effect size is, where you got that effect size from, the number of people to achieve adequate power. Pretty easy, straightforward. The hardest thing with these power analyses write-ups is going to be where you got this effect size estimate from and explaining to your readers where you pulled this information from. Sometimes it'll be sort of average effect size across this or that, or if you have a meta-analysis, that's awesome, or you can say effect size estimated based on test statistics provided by this person if you had them sort of back translate a T or something along those lines. But for the most part, the power write-up is pretty straightforward. Okay. People know? Okay. Yeah. Thank you. Yeah. Thank you. Like last time, was it your cohort? No one knew who He-Man was?
It was the one before.
One before. Like no one knew it. They just thought I was just posting like muscular naked dudes up there with swords, and they was very confused. Like this He-Man, the page boy haircut. It's hard to pull that off these days. But
He did 5.
What's up?
I said he did it 5.
Yeah, he did right. He's got a He-Man thing. Okay. So this is where. Alicia, we get into your question. So what happens if we fail to reject it null once we've run our power analyses and we did our due diligence, right? We went through, we estimated, got a reasonable effect, so based on everything that we could, and we still have failed to reject our test or our null when I think I have an adequately powered study, right? One, we have an error in our power calculations, right? I sort of just made a mistake somewhere in there, right? This is what Sean's beef with G-Power is that to make certain assumptions that often don't hold true for more complicated types of analyses, particularly within the context of repeated measures. And so if I just take what I've got from G-Power and then I run it, it could be that that was all wrong and I actually didn't run my power calculations correctly. This whole non-centrality parameter issue is a hard thing mathematically. It's become easier. We've had tools that have come online just because of computer power and things like that, but it's still, there's still a lot of fuzz in terms of the best practices and how to go through and do this. So we might have made an error in our calculations. Other thing that happens is our effect size might be smaller than what we had estimated. Why might this happen? Okay, so I went through and I looked and I pulled 3 or 4 different studies, and I said, on average, this is about what the effect size is in the published research. Why might I still find that my effect size, or why might it happen that the actual effect size I'm looking for, the population effect, is smaller than what's